any product then of spin orbitals that you write, okay, that describes 2 or more electrons would have to be asymmetric, like F3 and F4 that we did, okay? That's asymmetric. That won't be acceptable because it tells you which one is electron 1 and which one is electron 2, okay? But you can make linear combinations that are asymmetric, antisymmetric. So you want functions that are antisymmetric. So let's look at this one. What did we say F3 was? Electron 1 is spin up, right? Electron 2 is spin down. So this is F3. And F4 here gives you electron 1 that is spin down, and electron 2 is spin up, right? So if you want a 50-50 chance that it's either F3 or F4, what would you do? You can write your psi as 1 over square root of 2 F3 plus 1 over square root of 2 F4, right? Remember the square of the coefficients. In this case, 1 over square root of 2 squared would be 1/2. Gives you the probability. So the square of this is 1/2. The square of that is 1/2. So there's a 50% chance your system is described by F3. There's a 50% chance it's described by F4. Okay, so that might be an acceptable linear combination. Now, well, is that linear combination symmetric or antisymmetric? You have to make sure it is antisymmetric. So let's check. What would happen if I were to switch labels between electron 1 and 2? What would happen to my F3? This becomes a 2, that becomes a 2, that becomes a 1, that becomes a 1. That's still going to be F3, right? Right? 1s2, or is, no, that's not F3, that's going to be F4. We know it's asymmetric, right? That gives you F4. So this is 1 over square root of 2. F3 now becomes F4. What if we switch labels between electron 1 and 2 here? So this is now 2, that's now a 2, that's now a 1, that's now 1. So if we switch labels for electron 1 and electron 2 in function F4, what do we get? We get F3. So this is now going to be 1 over square root of 3, square root of 2, F3. Well, that's the same side that you have originally, right? So is this acceptable or not? This is not acceptable. Why? The function is symmetric. It follows the principle of indistinguishability, but it doesn't follow the Pauli principle. Yes?
Wait, this is symmetric now?
This is symmetric. So it's not acceptable. We want our function to be anti-symmetric. So we want, if we operate P12 on psi, we want to get back negative psi. So let's try to do another linear combination. What if I were to write psi equals 1 over square root of 2 F3 minus 1 over square root of 2 F4? What would that be? So if I were to operate the permuting operator, exchanging labels for electrons 1 and 2, on psi I get 1 over square root of 2 F4 minus 1 over square root of 2 F3, which is the same thing as negative of 1 over square root of 2 F3 minus 1 over square root of 2 F4. That's negative psi. That's the acceptable function. Okay, so for the ground state, when we say that our ground state of helium is 1s2, the function that we are actually referring to is not one of those functions we wrote earlier. The function we are referring to is this linear combination right here. So what's our psi going to be? We write it fully. I can write 1 over square root of 2. Okay. Electron 1 spin up. All right, electron 2 spin down, right? 1s2 beta 2. So this is your F3, right? Minus electron 1 spin down, electron 2, 1s2 alpha 2. This is F4. So this is the wave function that's associated with what you would call the 1s2 configuration. It represents, okay, a situation where you have two electrons in the 1s orbital. One of them is spin up, the other one is spin down. You don't know which one is spin up, you don't know which one is spin down. There's 50% chance, if you can give them names, you know, there's 50% chance electron 1 is spin up and electron 2 is spin down, or electron 1 is spin down, electron 2 is spin up. Okay? So that is the complete expression. Now, fundamentally, this function is still of the wrong form. It will not give you the exact energy because we have ignored electron-electron repulsion. Okay? This is the correct form if electron-electron repulsion could be ignored. But we have to, but the approach we're going to take basically here is that we'll take the electron-electron repulsion term as a perturbation. Okay? Now, we can improve upon this function. We can get better energies by doing a variational calculation in the sense that you could, instead of using the actual nuclear charge, realize that the presence of the other electron would make the other one of the electrons feel less of a pull from the nucleus. So instead of using Z equals 2, we can use an effective value for Z, call it the effective nuclear charge. So you get a better approximation of the correct energy. But, so that's a variation, you apply the variation method there. But still, you're not going to get the exact energy because fundamentally, we have ignored that electron-electron repulsion term. So mathematically, this form of the equation will not give you the exact energy. Okay? So let's see if we can factor things out here. Minus 1 over square root of 2. I can factor out what's common between these two. 1s1, 1s2, 1s1, 1s2, right? So I can write 1s1, 1s2 times alpha 1, beta 2 minus beta 1, alpha 2, or alpha 2, beta 1. Okay. So this is another way of looking at it. They're both in the 1s orbital, right? Both electrons in the 1s orbital. It's 50% chance electron 1 is spin up, electron 2 is spin down. Okay? And let me rewrite this as beta 1, alpha 2. And there's a 50% chance that electron 1 is spin down, electron 2 is spin down. And that minus sign there is what makes it antisymmetric.